we are looking at lesson 4 for unit 4, linear functions. Okay, if we look at our standards, our first standard, 8F1, is actually the same standard that we've been using through each of the lessons for this unit. 8F3 and 8F4 are new. We're just going to be seeing a little bit of each of those. 8F3 basically says there's an equation, and that equation creates something called a linear function. And we'll look at more into that as we go through the lesson. 8F4 basically is saying that you can model a relationship between two quantities, a linear relationship, by looking at something called rate of change, by using a table and a graph, and that's a lot of what we'll be looking at today. Okay, our mathematical practices are 1, 3, 4, and 7. Make sense of problems and persevere to solve them. Construct arguments and critique the reasoning of others. Model with math and look for repeated reasoning. And let's take a look at what we're going to learn today. So you're going to represent a function by writing an equation for it, making a table, and then graphing it. So we have been doing a little bit of this throughout the other lessons. Today is going to take all of what we've learned so far, put it together with real-life situations. Okay, let's look at our first situation. They hit you with a big one here, but we're just going to take it step by step. It's a real-world link. You're going to want to look at your worksheet for this. The Lockheed SR-71 Blackbird, that's a plane, has a top speed of 36.6 miles per minute. If x represents the minutes traveled at this speed, the function rule for the distance traveled is y equals 36.6x. Okay, so if we take a look at this, x represents the minutes traveled at the speed, and it says the function rule for the distance traveled is y. So my distance traveled is represented by y, and x represents the minutes. Okay, and my formula, or my equation, is y equals 36.6x. Now if we take that and apply it to something that you do know, and let's say you're looking at speed of a car. Okay, a car, if you're driving 60 miles per hour, you don't need to write this down, just watch. If you're driving 60 miles per hour, your distance is going to equal your speed times your hours, or x. Okay, so times how long you've driven. So if you've driven for 1 hour, so if x becomes 1, at 60 miles per hour, if you've driven for 1 hour, that's going to be 60 miles. If you think about it, 60 miles per hour means in each hour I'm driving 60 miles. In 2 hours, it's 120 miles. In 3 hours, it's 180 miles. And what I'm doing is I'm multiplying my speed times my hours. And that gives me my distance. Okay, same exact type of situation, except this case we are looking at this Blackbird. So my equation right here is telling me that if I take my my minutes, or x, and I multiply by the speed, I will get my distance. Okay, now the reason that they chose y for the distance and x for the speed is because, or x for the minutes, is because you would multiply speed times minutes to get the distance. And whenever you see our equations, what you're going to notice is it's going to be y equals something. Okay, just like in the last lesson it was f of x. F of x is the same thing as y. Okay, so that's something common that you'll see through each of these activities. So if we complete this table, what you want to do is you want to take a look at the rule. So our input is our x, then our rule is our 36.6 times x. Our output is the y, okay, and that's going to be our distance. And then we end up with an ordered pair. So if I look at 2 here, 36.6 times 2 is 73.2. Okay, and so my ordered pair would be 2, 73.2. So what I want you to do is, if we take a look at 3 now, our rule is 36.6 times our minutes. Go ahead and determine the output, write your ordered pair, and then I want you to do 4 all by yourself. So hit pause and then complete the table. Okay, now check your table compared to mine. I went off my screen just a little bit here. Because in our next section, oops, the next section here, it says graph the ordered pairs x, y on the coordinate plane provided. What do you notice about the graph? So if we take a look at our x and y axis, we need to label them. Whenever you have a real life situation, you want to label the x and y axis so the people looking at the graph can determine what's happening. So if we look at our x values, our x stands for what? Take a look back at the problem. What does the x represent? Hopefully you got minutes flying, or just minutes. Our y variable, or our y axis, is going to be our y represents the distance. You could even say miles. Okay, you could say distance or miles. Now, when you're graphing these points, we do have some decimals, so you're going to want to plot them as close as possible to the numbers that you have. So if my first ordered pair is 1 and 36.6, I go over 1, and now 30 is going to be in between 20 and 40, but it's going to be closer to 40 because it's 36.6. So it'll probably be somewhere up there. My next ordered pair is 2 and 73.2. It's going to be somewhere in between 60 and 80, a little bit above middle. Okay. My next one, 3 and 108 or 109.8, so I go to the right 3. And up 109.8, so it's going to be right in the middle of 100 and 120. And my last one is 4 and 146.4, so it's going to be just a little bit, not quite half, but a little bit lower. It's hard to graph with what I'm using right here, so you'll probably get a little bit better than me. But this is very close to what your graph should look like. Now it says, what do you notice about the graph? So I want you to take a look at these points. And I want you to pause and think about what you notice. Any observations that you could possibly make about what's happening in this graph, write those down. So hit pause. Okay, some ideas of what you could have written. You could have written that if you connected those points, it would make a straight line. You could also have seen from left to right, if you notice that the points are going up higher. Okay, as the minutes go up, the distance goes up. As the minutes increase, the distance increases. Okay. So any type of observation is what I want you to write. Okay, the next little section just gives you some information about graphing a function. It says sometimes functions are written using two variables. One variable, usually x, represents the domain. We already know that. And usually the y represents the range. When a function is written in this form, it's an equation. Okay. Like equations, functions can be represented in words, in a table, with a graph, and as ordered pairs. The graph of a function is the set of ordered pairs consisting of an input with a corresponding output. Okay. So our input with our corresponding output gives us ordered pairs, which we can put on the graph. Oops. Sorry about that. Wrong slide. Okay, the reason that they just went through that about graphing is because in our next example, we're going to be creating a function table. Okay, we'll have an equation. We're going to choose x's, get y's, create ordered pairs, and graph them. Okay, so let's take a look at example 1. The school store sells book covers for $2 each and notebooks for $1. Tony has $5 to spend. The function y equals 5 minus 2x represents the number of book covers x and the notebooks y she can buy. Graph the function, interpret the points. Okay, so a couple things about this. They give you all the information that you need. Obviously, you can see the whole example's done. But I want to talk about what's happening here for a second. If we look, if you look at this equation, one of the things is, how do you know the y is represents notebooks and that x represents book covers? Because if you notice here, book covers is x, notebooks is y. Okay, one of the reasons is something's got to be the y. Got to pick one of them. And, you know, one idea might be because the notebooks are $1. So when we do our formula work, whatever y equals, if it's y equals 10, because each of the Ys or the notebooks cost $1. If I have 10 left, I know it's $10. So mathematically, it's a little bit easier because the Y has a value of $1 per notebook. Okay. If we take a look at where this 5 came from in our equation, the 5 comes from the fact that we have $5 to spend. So if I have $5, I'm going to take away $2 for each notebook that I purchase. So if I purchase one notebook, I take away $2. If I purchase 2 notebooks, I take away $4. 3 notebooks, take away $6. Okay, so I have my 5. I take away $2 for every notebook, or for every book cover, and that leaves me how many notebooks I can have. Okay, so that's where everything's coming from here. A little side note on the left, what you'll notice, is this equation y equals 5 minus 3x could also be written, instead of a y, you could write f of x, and that you saw that a lot in the last unit, or the last lesson. Okay, so step 1. In step 1, we chose x values. I want you to take a look for a second at these x values that we chose. Okay, think about what x represents. X represents the number of notebooks purchased. The numbers you choose, you want those to be appropriate for the situation. So would negative numbers be appropriate? Think about it. Could you have negative notebooks that you purchased or book covers? I don't know. Okay, we started at 0. Could you purchase 0 book covers? Absolutely. If she purchases 0 book covers, I have $5, take away 2 times 0, because that's 0 book covers, and she is left with a 5. Here's what that means. Y is the number of notebooks. So if I buy 0 book covers, I can buy 5 notebooks. Okay, let's look at 1. If x is 1, that means I bought 1 book cover. If I buy 1 book cover, I plug in my formula, 5 minus 2 times 1, and I get 3. So if I buy 1 notebook cover, I can purchase 3 notebooks. Next one, if I buy 2 notebook covers, $5 minus $2 for each of my 2 book covers, and I'm left with 1 notebook I can purchase. And the last one, if I buy 3 book covers, I insert my formula, 5 minus 6, because if I buy 3 book covers, that's going to be $6. I'm in the negative. I want you to stop and think about that for a second. Does that make sense? Is that possible? Okay. So some things to think about when we're creating a table. Some numbers are more reasonable than others. How about a decimal or a fraction? Could I have chose a fraction for my x? Could you buy a fraction of a book cover? Something to think about. Now for the graphing. Okay, we're on our graph at this point. It says graph the ordered pairs. So if we look at our ordered pairs, do you notice this is down in a negative area? Okay. If this y represents number of notebooks, I can't have a negative amount of notebooks. Okay, that's a problem. If we look at our note here, she cannot buy negative amounts. So she can buy 0 covers and 5 notebooks, 1 cover and 3 notebooks, or 2 covers and 1 notebook. So if we look at these 3 right here, those are the only 3 possibilities of what kind of combinations of purchases that she can make. If I continued to the left, I would end up with something else in the negative. Okay, that wouldn't work either. Okay, so now's the point where I want you to answer a couple questions based on what I talked about with that example. So in the sidebar, I want you to write and complete the following statement in your own words. 0, 1, 2, 3 were reasonable numbers to choose for x in this example because. Now we do know there was an issue with this 3. However, when we started the table, for all we knew, 3 would be a reasonable number. Why is that? Okay, so we know that in the end, 3 didn't turn out okay. But in the beginning, when we just chose x's, or when the book chose the x's, 3 seemed reasonable. Why? Why did 0, 1, 2, and 3 seem like reasonable numbers to choose from the start? Okay. You can also always add a side note about why the 3 ended up being a bad idea. And then the second statement is I would not choose negative x values because. So why would you not choose a negative number for x? If you would have chosen one, wouldn't have worked out. Why would that not have worked out? Think about it for a minute. And I want you to write in the sidebar. You'll want to hit pause.
Graph a function. There are many ways to represent a function. One way is with a graph. Let's graph the function y equals x plus 2. Select several values for the input x. We'll use 4 values: 0, 1, 2, and 3. Substitute these values for x to find the output y. 0 plus 2 is equal to 2. 1 plus 2 is equal to 3. 2 plus 2 is equal to 4. And 3 plus 2 is equal to 5. Now that we have our y values, graph each ordered pair. The first ordered pair is 0, 2. The next pair is 1, 3. Now we have 2, 4. And the last ordered pair is 3, 5. The points appear to form a line. Draw a line that passes through each point. The line is the complete graph of the function. The ordered pair corresponding to any point on the line is a solution of the equation y equals x plus 2. Now, let's check our work. It appears that the ordered pair negative 2, 0 is also a solution. We can check this by substitution. First, write the function y equals x plus 2. Now replace x with negative 2 and y with 0. Finally, we simplify. 0 equals 0. So negative 2, 0 is also a solution of y equals x plus 2. In conclusion, we have represented a function in 3 different ways: an equation, a table of ordered pairs, and a graph.
Okay, oops, hold on, let me move my slide here. Okay, here we go. So let's take a look at an example on our own. Example A says, the farmer's market sells apples for $2 per pound, oranges for $1 per pound, and Marjorie has $10 to spend. Our equation is y equals 10 minus 2x. Okay, $10 is the money she has. $2 per pound, so this is pounds of apples. Not the 2, just the x. So the x is pounds of apples. The 2 comes from price per pound. And my y is number of oranges. Pounds of oranges. This would actually be a 1y because it's $1 per pound. Okay? So in this case, the 1 would be price per pound. Okay. If you need to add those notes, pause this and copy that all down because I'm going to erase it here in a second. But just so that you can see the breakdown of each piece of this equation, that's going to be important because eventually you're going to be creating your own equations from a situation. You're not going to be given the equation. So you might want to stop and pause and label everything so that you see where everything came from. So do that now if you need to. Okay. So, graph the function and interpret the points. Okay, so the first thing we're going to do is we're going to create a table, choosing some x values, take our formula, 10 minus 2x, get our y, and end up with ordered pairs that we're going to graph. Okay, so let's think of some numbers that are reasonable for our x values. Would we want negatives? No, you can't buy negative pounds of something. Okay, so that we're agreeing we're all positives or 0. Decimals and fractions. You could buy a fraction of a pound. Absolutely. You could buy half a pound of apples. I would avoid it just because I don't want to deal with fractions or decimals unless I have to. So I would stick with whole numbers, but do keep in mind we could use decimals if we wanted to. Last problem, we could not because you can't have half a book cover. In this case, though, you can have half a pound. That is acceptable. However, I don't want to deal with that. So I'm going to pick 0, 1, 2, 3. Go nice and small. So x is my pounds of apples. So my first formula, I'm going to say $10 minus $2 per pound of apples. I bought 0 pounds, so that's 0. 10 minus 0 is 10. So if I buy no apples, I can buy 10 pounds of oranges. So no apples, 10 pounds of oranges. If I want 1 pound of oranges, I take the $10, subtract $2 for each pound, which is 2. That leaves me with 8. 1 pound of apples means I can buy 8 pounds of oranges. 2 pounds. I have $10 and I'm going to subtract $2 per pound. I have 2 pounds, so that's $4. 10 minus 4 is 6. 2 pounds of apples, 6 pounds of oranges. And my last one, if I take 3 pounds, $2 a pound, that's $6 that I take away from my 10, and I'm left with 4. Okay? A couple things I want you to notice to help you self-check as you go through. If we notice if there's a pattern with our x values, there should be a pattern with our y values. As my x values increase by 1, what happens to my y values? They're decreasing by 2, and the reason they're decreasing by 2 is because it's $2 a pound for apples. So every extra pound of apples I have, that's $2 more I'm spending. 2 less dollars I can spend on oranges. Okay? So now if we take a look at our graph, we're going to label our x and y axis. Our x is pounds of apples, and my y is pounds of oranges. LBS stands for pounds. And I'm going to graph. So if my x is 0, my y was 10. At 1 pound, I was 8 pounds of oranges. Now I have to put that in the middle. My graph isn't perfectly on. You'll have to make sure that yours is correct. 2 pounds of apples means I can buy 6 pounds of oranges. 3 pounds of apples means I can buy 4 pounds of oranges. Oops, that's a horrible dot here. Okay. You'll get the point on mine. You make sure that, don't forget my intervals go by 2s. So if I have 3 pounds of apples, I've got to put it in between the 2 and the 4 here. Okay, so keep that in mind. All right. So it says graph the function and interpret the points. So take a look at these points, and I want you to think about some observations you can make. So the table, find a spot for your table, and then where it says A right here is where I want you can draw the table in there if you can fit it. But that is where I want you to interpret this graph. And what we mean by interpret is make some observations. What do you notice about those points? Okay. The other thing you could think about is, could I have some points in between? Could I say 2.5 pounds, 2.1 pound, 2.2 pounds? Anyone that's been to the grocery store, you've seen your fruit weighed or your vegetables. There's all different kinds of points in between. Keep that in mind as well. Do the points look like they're increasing from left to right or decreasing from left to right? If you're unsure what that means, think about what increase means and what decrease means. Okay. Maybe as the pounds of apples increase, what happens to the pounds of oranges that we can get? So think about all those things and come up with some sort of interpretation of what you see. So now let's take a look at another example. Graph y equals x plus 2. Okay, they give us all of our information here. Step 1, make a function table. Select any 4 values for the domain x. Substitute them in for the x, find the value of y, write the ordered pairs. Now here's the deal. If you're just given a straight equation, the x values don't matter. You can pick positives, you can pick negatives, you get to pick whatever you want. Think strategically though. If I pick positives, I'm adding 2 to my x. So that will make my numbers get larger as I go. So picking positives is a good idea. You won't really run into negative number situations. Don't forget you're going to be graphing these, so you would not want to pick like 100. It's going to give you big, huge numbers that now you have to deal with on a graph. So think strategically when you're choosing your x's. What they're doing in your worksheet is usually what I would do. Pick low numbers, pick numbers close to 0. It just makes the arithmetic a little bit faster, more efficient. So take a look at the table and see what they did. Make sure you understand how each number came to be in each row and column. And then check on the graph, make sure that all makes sense. Because the important part is what's written in this box right here. It says the line is the complete graph of the function. The ordered pair corresponding to any point on the line is a solution of the equation y equals x plus 2. Okay, up to this point, you saw the word, when you heard the word solution, it meant that when you had an equation, you solved it and you got a number for the variable. So if you had x plus 2 equals 5, you knew the solution was x equals 3, because the only option you had was for x to be 3. That was it. Once in a while you had many or none. There were special cases. But usually if you were given an equation, you had to find the missing variable. Well, now we have equations with an x and a y. And what will happen is if you choose an x, you get a y. This ordered pair is now the solution. Okay, so that ordered pair is now the solution. We have an x and a y that match each other. A coordinate, they coordinate. When x is 0, y is 2. Okay? So each of these points is a solution on your graph. So what I want you to do in the sidebar, right, or actually you're going to do something else in the sidebar in a second. But somewhere up around this example area, I want you to write each ordered pair is a solution. And you'll notice on the little sticky note on the side says that as well. The solutions of an equation are ordered pairs that make it true. I do want you to write this on your own, though. I want your hand to do that. Now, if you notice down below, there is a check. Take a look at that. It says it appears that negative 2, 0 is a solution. Check by substitution. So what you do is you substitute the x with negative 2, the y with 0, and see if it checks out. Just like if you had x plus 2 equals 5 and you said x equaled 3, I could check it by plugging the 3 in and saying 3 plus 2 equals 5. Yes, it does. Okay, you can check the same way, even though you have an x and a y. Substitute the y with a 0, x with a negative 2, and see what happens. This checks out, so that's the solution. So every single ordered pair is a solution. The other thing you're going to notice is there's a straight line connected. The reason there's a straight line connected is because if I chose a number, the number 0.5, if I chose 0.5 for an x, I'm going to get a number for y. And what will happen is if I were to choose every single decimal in between 0 and 1 for the x, I would get tons, like basically infinity little points. And all those points together connect up to make a straight line. Okay, now in this sidebar area, I want you to take a look at these two statements. I can check that my table is correct by blank. I can check that my graph is correct by blank. Okay, a couple things I want you to think about with your table and your graph. With the table, something that I mentioned in the last example is you should see patterns in your table. If the x values have a pattern, your y value should also have a pattern. That could be one way you check. Maybe you want to go through and do a check on each ordered pair. You want to plug the ordered pairs into your equations to double check that you did your arithmetic correctly. That's up to you. Checking your graph. We've been talking about these linear equations create straight lines. If you don't have a straight line, is there a problem? Okay, I want you to take a look back at the last example really quick. This created a straight line. Okay, what I would suggest to you is when you're making your tables, what you'll notice is they always pick 3 or 4 numbers. The reason is if you pick 3 or more numbers, any error will stick out like a sore thumb when you're graphing. If I would have done some arithmetic incorrect, like let's say I did the 2, 4, and I got 2, negative 4, that would put my point down here. So let's say I had 1, 2, 3 up here, and then the 4th one at the bottom. See how it sticks out down there? That means that there's an issue right here. There's something wrong. I would need to double check my arithmetic for that ordered pair and make sure I didn't make some sort of mathematical error. So when you're graphing these, what's really nice is the points connect up to make a straight line, and if you don't, whichever point is sticking out to the side somewhere it doesn't belong, you know that's the number that's an issue and you can fix it in your table. So in your own words, I want you to write these statements and finish them in the sidebar. The last thing I want you to write in the sidebar is this. 0, 1, 2, 3 were reasonable numbers to choose for x because y. We talked about choosing numbers. These are good numbers to pick, not necessarily the best, but why are they reasonable? Okay, I want you to try these out. I will do B with you. So first thing we'll do is make a table. We're going to choose x's, then we're going to put the rule, get our y, and then end up with ordered pairs. So you can pick whatever x's you would like. I would say, if you notice, I only go down to -3, but I go up to 8. So I would definitely choose some x's that fall within the coordinate plane that they give you. I always like the beginning. So 0 minus 5 is -5. 0, -5. 1 minus 5 gives me -4. 1, -4. 2 minus 5 is -3. I get 2, -3. And then my last one would be, 3 minus 5 is -2. 3, -2. Okay, a couple things we can check. As my x's increase by 1, each of my y's are also increasing by 1. -5 goes up to -4, goes up to -3, goes up to -2. So since I'm seeing a pattern, that's a really good sign that I chose the right, I did the right math. So let's plot our points. 0, -5. 1, -4. 2, -3. Over 3 down -2. And what you'll notice is these points are very nice to create a straight line with. That's what you're going to do on B. I want you to try C on your own, so hit pause and go ahead and see if you can get C done by yourself. Okay, so take a look at C. You might have chosen different numbers for your x. If you chose the same numbers as me, what you may have noticed is when you got to x equals 3, 3, -6, you ran out of room on your coordinate plane. As long as you have those 3 points, you should have been okay getting that line drawn. Your line should be exactly like mine. It should go through the origin, be tilted about the same. If you chose, x is -1, you got -1, +2. If you chose x was -2, you would get -2, 4. Okay, those are pretty much all the ones that you could choose to stay on this coordinate plane. A couple things to notice. As my x's increase by 1, what happens to my y's? My y's start doubling. 0 double, well, actually doesn't really double. -2 times 2 is 4, or added to 2. Sorry. 0 minus 2 is 4. -2 minus 4 is -4. -4 minus 2 is -6. Okay. The other thing that I want you to be aware of, you're not always going to have an addition or subtraction problem in your equation. Your rule might sometimes be a multiplication problem like we had here. Okay, the last thing we're going to look at in this section is this key concept. Okay, so up until this point, we could show functions with a table, with ordered pairs, and with a graph. We had done that already. Now the new thing we added was an equation. Okay, they did put it in words here, but do know that each of these 5 representations is a way that you can show a function, using words, using an equation, a table, ordered pairs, or a graph. Okay, we are going to pause on this continuous and discrete section. However, I do want you to put this linear function in your vocabulary. But we will come back to the continuous and the discrete data. Okay, we will come back to example 3. Fast forwarding through this section. Let's go back. We're fast forwarding through this as well. Don't worry about continuous data for vocabulary. And don't worry about discrete. We will come back to those later. Linear function, make sure that's on your vocabulary page. You can put it on the page from last week. Okay, let's take a look at the guided practice. Graph each function. Go ahead and hit pause. I want you to try these on your own, and then I will put up some examples. What I do want, you can say, I'll help you get this started at least. X plus 5, Y, and you can have an extra column for your ordered pairs if you would like. That's up to you. X, our formula is 3x, our equation is 3x minus 2. Okay. You can choose your own x's. I will give you some x's if you don't want to pick on your own. What I do want you to notice is our x coordinates here. Most of them are negative, so let's keep it in the negative area. I'm going to say -2, -1, 0, 1, and 2. These are usually the numbers I would pick just because it keeps you around the origin and you don't need to have a huge coordinate plane most of the time. And then for this one, they're letting us do whatever we want here from -5 to +5. But I like the negatives. So these are the numbers that I'm going to show you. You can choose different if you'd like. But go ahead and hit pause and try this on your own. Okay, so if you take a look at number 1, what you'll notice when you graph your ordered pairs is that you should get a straight line that looks like mine. It should go through the y-axis here at 1, 2, 3, 4, 5. It would go through your x-axis at -5. Okay. Goes through the y-axis at 5. So those are 2 points that you can take note of. Okay, so your line, if you laid your paper on top of mine, you should have at least part of the same line. You may have, this section right here. Okay, that might have been your line. Or maybe this was your line. But ultimately, this piece right here, somewhere along here is where your line should be. Okay, so pause again if you want to try number 2 on your own. Okay, now the second one was a little tricky. What I had to do was I had to extend my table because I just needed a little more area for work, just because I had so many negatives. And you may find that too, is that the space in the table isn't big enough. So adjust how you need to adjust. I wanted to make sure that when I was working these problems out right here, I wanted to rewrite it as I wanted to follow those order of operations and get -6 minus 2. You may have even wanted to add the opposite on these. Okay. The other thing that you might notice is depending on the numbers you picked, my first ordered pair was going to be -2, -8, and that was not going to fit, so I had to graph these 4. Was all I could graph. Ultimately, your line should look just like mine. Okay. Now for number 3, we are going to eliminate C, but we can do everything else. A satellite cable company charges an installation fee of $50 plus an additional $35.95 per month. Write a function to represent the cost of any number of months of service. So total cost. Total cost means that's our final number. So that's going to be our Y. So Y is total cost. Cost always equals some sort of formula that happens. Okay, so my total cost, so cost will be Y. And so that means if we take a look, my installation fee is $50 plus $35 per month. A couple things. Anytime you see the word per month, per day, per hour, per anything, that's multiplication. 60 miles per hour. Okay, $35.95 per month. If it's 1 month, it's $35.95 times 1. 2 months, $35.95 times 2. 3 months, $35.95 times 3. So it's $35.95 times the months, which is X. Any number of months. So Y is cost, X is months. So you'll want to add that to the side. Y equals cost, X equals months. Okay, so let me rewrite this a little bit here. So my total cost is Y. Sorry, let me make some room so that you could tell the difference of what's what. So total cost is Y, and it's going to be $35.95 for each month. Okay, so I'm going to multiply by my months, plus this $50 fee that's going to happen once no matter what. Okay, the reason this $50 has no variable with it is because that's only going to happen one time. So just $50 one-time fee. Okay, so my function is y equals $35.95 x plus the $50 fee. Make a function table to find the total cost for 1, 2, 3, 4, and 5 months. So my formula is $35.95 x plus 50. So take a second, grab your calculator, and calculate each of your fees for the month. Okay, now my pen is big, so I didn't do this section here. But what you should have found is that for 1 month it cost $85.95. Okay, that's by the end of the first month how much they've paid. By the end of the second month, they've paid $121.90. Now, the one thing I want you to keep in mind, this doesn't mean the second month their bill is $121.90. This is saying that at the end of the second month, they've paid so far in total. So for all the months they've paid so far, their total payment has been $120.90. After the third month, they've paid the cable company a total of $157.85. Okay, that is not their third month bill. That's just what they've paid the company so far in total. Okay. Now C, they want you to graph and explain, interpret it. So if we look at our x coordinate is months, and our y coordinate is cost. So you're just going to have to do your best at getting your points close to where they need to be. Mine is going to be difficult because my pen is big and my screen here is small, but you'll be able to get the point. 3 months, it's about 156. 4 months, about 198. And what you'll notice, yours should be better than mine. Oops, my 4 is off. Let me fix this a little bit. What you should notice is it does make some sort, if you should be a little more perfect than me. These points do look like a straight, they could make a straight line if you connected them. Now think about, okay, now the one thing I want you to think about, C asks you if it's continuous, so don't worry about that. But what you can think about is, could you connect these points? Could I have a half of a month? Would you pay for half of a month? Does cable get charged half of a month? I don't know, maybe it does, maybe it doesn't. Think about that, something to just think about. But D wants you to interpret the graph. What do you notice about the points? Okay. And then number 4, how can functions be used to solve real-world situations? That's up to you. You decide how you want to answer that question. That's it. So head over to the self-check that you see posted online and see how you did.